Okay, in the interest of having this upload in a reasonable span of time, I hope, I'm going to try to keep this to one picture and an audio file. I would have rather done this as a video so I could kind of go through things step by step here, but I'm going to try this. I wanted to back up and sort of just go into what motivates even the idea of doing complex numbers. I thought about starting sort of from the end and talk about all the things that complex imaginary numbers, things that have this number I, which functions as the square root of -1 in them, all the things that they let us do in the modern world. I'll briefly mention that every class on electrical engineering that I took at Berkeley was absolutely dependent on the idea of the square root of -1 as part of the class. Almost no analysis of anything with a frequency, anything that oscillates would be possible in modern physics, modern engineering, without the concept of I, the square root of -1. In electrical engineering, we actually used a J because we were already using the symbol I for current, and we needed to use a different symbol, but it was still the same thing. It was still a number that when you squared it, you got -1. Backing up from that, though, going down this little sheet that I made up. So if we look at the first four equations, x, 1, 2, 3, 4 there, x plus 2 equals 5, x minus 2 equals 5, 2x equals 10, x over 2 equals 5. All of those can be solved with natural numbers, as they're normally called, just the counting numbers, basically. The first one is obviously x would come out to x is equal to 3. In the second one, x could be equal to 7. In the third one, x could be equal to 5. And in the fourth one, putting x equal to 10 would give us something. If x is 10, then when 10 is divided by 2, we'd get 5. So x equals 10, basically. So all of those things are natural numbers, natural counting numbers. And for a very long time in mathematics, those were the only kind of numbers that anybody talked about, the only kinds of numbers that anybody accepted as existing. For maybe 1,000 years, human beings were doing some fairly sophisticated mathematics, but those were the only kinds of numbers that they were dealing with. There is actually an awful lot that you can do with those kinds of numbers. And then, going slightly out of historical order here, at some point somebody wrote down an equation like the one that I've got the star next to here. Basically doesn't look that different from equation number 1 when you look at it. Only one number is changed from the equation I've numbered number 1 and the one that I've given this special little star to. And yet, for, again, over 1,000 years, most mathematicians would have said the one with the star in it is nonsense, doesn't make any sense. There cannot possibly be a number x that would satisfy this equation. It's debatable exactly when people started thinking in terms of abstract algebra equations, but the idea would have still been there. Find me something that I can add to 5 that when added to 5 still just gives me 5. For 1,000 years, the most brilliant minds on the planet would have insisted that's impossible, that's nonsense. And then somebody decided, no, maybe it wasn't nonsense, and we ended up with the concept of 0. Having a symbol that represents nothing. And I seem to remember seeing somewhere, it might have even been in the How We Got to Now book, where they talked a little bit about, even once there was a symbol for 0, for a long time people treated it as weird and special and totally different from other numbers, and you couldn't just do whatever you wanted with it. Now we just treat it more or less like another number. Okay, moving along. So in 1a and 2a, some of what I've done with the numbering of these equations is kind of arbitrary, but to solve x plus 5 equals 2, or to solve 2 minus x equals 5, suddenly we've jumped into negative numbers. In order to get that to work out, to get the 1a equation to work out, x is going to have to be negative 3. So that when you add it to 5, you get 2. In order to get the second one to work out, negative x is going to have to be equal to 3, which means that x itself is again going to have to be negative 3. So in getting into the whole thing on imaginary numbers, and I know this is probably not exactly what you wanted to hear, I will get into more of what imaginary numbers are useful for later, but I've always kind of wanted to go through it in this way with somebody, so you're the victim. It's a question even I asked in high school. Are imaginary numbers real? Do they really exist? And much as I was enjoying learning about them, I did question, is this ever going to be useful? How is this going to be useful? But a good analogy is to look at negative numbers. In some contexts, negative numbers make sense. If you're talking about a temperature, a negative temperature makes perfect sense. If you're talking about a bank balance, a negative number, while distressing, makes perfect sense. If you're talking about a length or an area, a negative number makes much less sense. And yet, in some cases, using negative numbers in the equations that go into designing a house or a beam can actually allow you to get a solution that is real and meaningful. Or to reject some solutions and realize, oh yeah, that's a solution of the equations, but it doesn't mean anything in the physical world. Saying that I can build a 100 square foot addition to my home if I just add a room that's negative 10 feet by negative 10 feet doesn't really make any sense or mean much of anything. So in a sense, the probably simplest answer that I can give to someone who's saying, are imaginary numbers real? I don't believe in imaginary numbers, this kind of thing, is, are negative numbers real? Well, in some contexts, yes, they have a meaning. A negative temperature has a meaning. In other contexts, they don't. In imaginary numbers are somewhat similar. They can definitely signify things that do end up having meaning for the real world. Does that mean that you're ever going to see a room whose square footage is equal to 5 times the square root of -1? No, that's not going to happen. It's not meaningful in that context. Moving right along. So in 3a and 4a, we get into rational numbers. There was kind of a time when those even were a little suspect among human beings. It's like, well, how can you have something where, looking at 4a, where you have to have 3 of something in order to get 2 of something? That's just crazy talk. We would now just say, well, the answer to that is 2/3, and it's perfectly normal and makes perfect sense. It's a rational number. one natural number divided by another one. Moving right along, because I've got to get this recorded so I can get it started uploading. People, again, playing with these equations, moving the numbers around, start doing things like, well, you could take a number and multiply it by itself. So could you have something where find me the number that when multiplied by itself and then multiplied by 2 gives me 18? Well, that's obviously x equals 3, so that works. And how about, a number where x cubed equals 27? A number that multiplied by itself and multiplied by itself again gives me 27. X is obviously 3 there. Great. And I've written kind of by the side here to solve this. You pretty much got x a member of the integers. At some point, someone decided that the integers, including 0, should be represented by this kind of funny-looking, fancy z character, which is relatively easy to get some printers to print, but not necessarily that easy to draw when you're doing it yourself. Then we come to what I consider to be one of the more interesting cases. If we do something like rearrange these equations, again, playing with the numbers a little bit, and we just say, well, okay, we've got, an easy solution to 2x squared equals 18. Well, if we just wanted to say x squared equals 7, find me a solution for that. And suddenly, this was somewhere apparently around the time of Pythagoras, the bottom dropped out of the world for the people that were first looking at this and realized that no rational number could solve that equation. They give a fairly lengthy, kind of involved proof of this in a lot of different math classes. To my mind, there's a much better proof than the one that's usually presented, which is a pretty simple one. Any rational number is basically just a reduced fraction, a over b. We see reduced fractions all the time. They taught us about them in school. You see something like 2/7 or 3/5 or 11/17. Any number of things where you've got one number on top and another number on the bottom, and they don't have any common divisors. As mathematicians like to put it, without loss of generality, we can assume that any rational number is simply the reduced form of it. We don't need to consider 4/10 because we know that's just 2/5 in another form. Any property that 2/5 has, 4/10 better have that same property, or something has gone very wrong somewhere. So if I can prove something about 2/5, I've proved it automatically about 4/10 because 4/10 is 2/5. Yeah, it was way over wordy on that. But so if you prove something about all reduced fractions, you basically prove something about all fractions because every fraction has a reduced form that is equivalent to the original one. If I've got a number like 7/49, I know that there is some fraction it reduces to, or it's already in lowest terms. Okay, so if we consider a reduced fraction and we say, well, I'm going to take this reduced fraction and square it, well, the top number, and this uses a thing that has the over grandiose name, the fundamental theorem of arithmetic, but it's something we kind of all, I think, by the time we've gone through school, intuitively know, and it's not too hard to see as one of those things that seems true, reasonably true, just by thinking about it a little, every number is basically either prime or composite. It either can be divided by other numbers or it can't. And the numbers that can be divided by other numbers, like say 24, can be broken up into primes in only one unique way. So 24 is equal to whatever it is, 2 times 2 times 2 times 3. If I've got a rational number represented as a over b, and yeah, I didn't actually think to write an a over b on the sheet here, then the top number has some unique representation as a bunch of prime numbers multiplying into each other. And the thing on the bottom has some unique representation as a bunch of prime numbers multiplying into each other. And there are no prime numbers in common between the ones on top and the ones on the bottom. I could write out a as being equal to whatever it is, 2 times 3 times 7 times 11 times 11 times 11 times 13. There's some unique set of numbers that goes together to be multiplied together that would make up a. And then whatever's on the bottom, if this is a reduced fraction, doesn't have any of those numbers that appeared on the top. If there's a 2 on the top, there's not going to be a 2 on the bottom. This is more confusing than it should be because I'm not actually doing a video with this, but it's probably, I hope, making sense. You know, I could have, if I've got a fraction and it's 10/27, let's say, then that's really 2 times 5 on the top divided by 3 times 3 times 3 on the bottom. It's already reduced because 2 doesn't divide evenly into 3, 3 doesn't divide evenly into 2, 5 doesn't divide evenly into 3, and 3 doesn't divide evenly into 5. 10/27 cannot be reduced any further, and the set of prime factors on the top is disjoint from the set of prime factors on the bottom. They don't have any elements in common. And when I square the whole thing, trying to wrap this up, what I'm going to end up doing when you square a number a over b, you end up with the number a squared over b squared. You can do a little bit of algebra and convince yourself of that. And when you do that, you're just going to take the set of prime numbers that were the factors of the thing on the top and basically write everything twice. And then you're going to take the stuff on the bottom and you're going to write all of its factors twice. So for my example of 10/27, when you square it, it's going to be 100/27 squared, which is 243, I believe. Sounds about right. And no, it's not. Let's see. 27 squared would be 27 times 3 would be 81. 81 times 3 would be 243. 243 times 3 would be 729. Okay, so it's going to be 100/729. But at any rate, the thing on top is now 2 times 5 times 2 times 5. And the thing on the bottom is 3 times 3 times 3 times 3 times 3 times 3. There's still nothing on the bottom that will cancel any of the things that are on the top. Nothing on the top that will cancel any of the things on the bottom. Now that you've squared it, it's still an irreducible fraction. The point of all that being that if I've got a number that's a rational number and can't be reduced, when I square it, it's still not going to be able to be reduced. As a result of that, you can pretty immediately see that if there's going to be any number that when it's squared is going to be equal to 7, it can't be a proper reduced fraction. Because if it's a reduced fraction, when I square it, it'll still be in reduced form and there won't be anything to cancel out. It's certainly not going to suddenly be an integer. The stuff on the bottom isn't going to cancel out. And it's going to be whatever a squared on the top over b squared on the bottom, and nothing's going to cancel. Yeah, I think I'm raving at this point. So the only way that a natural number can have a so-called rational square root is if it's basically, if it's an integer, if it's a natural number, if its square root is a natural number, if it, so that its denominator, if you want to call it that, if you're writing it as a rational number, is basically just 1. So 4 has a rational square root because its square root is an integer. But there is not a single integer that has a square root that is a fraction. The square root of 2 is not a fraction. The square root of 3 is not a fraction. The square root of 5 is not a fraction. For that matter, the square root of 4 is not a fraction either. It's an integer. It's 2. The square root of 6 is not a fraction. The square root of 7 is not a fraction. The square root of 8 is not a fraction. The square root of 9 is not a fraction either. It's the number 3. Anyway, so there is no number x that is what we would call a rational number that you can square and get 7. If you take the square root of 7 by the same token and wrapping this up really, the square root of 7 is, if you expand it as a decimal, it goes on forever and it never repeats. Any number that repeats can be turned into a fraction like 157 over 216 or something. That would eventually, the decimals would start to repeat. But the square root of 7, never. The decimals will never repeat in its square root. Okay, fine. And similar argument would apply to something like equation 6a, x cubed equals 7, and a whole host of things like this where we get into irrational numbers and discover there are numbers that we came up with a fancy little check box to looking thing to indicate the square root of 7 because there was no way of writing it down as a fraction as a over b. Great. Moving along, hopefully. This, and that though part was worth spending some time on because that basically gets us into the realm of the real numbers. Technically, it only gets us as far as the irrational numbers, but the irrationals are, I'm going to call it, a big part of the real numbers. There are people that would contradict me on that, but they can shut up. The irrationals are at least our first real step towards realizing that the real numbers exist and that they include a heck of a lot more things than just the integers and the fractions, the rational numbers. I wrote down the 5a prime and 6a prime to the right of all that just because it started being fashionable to put equations in kind of a standard form where you would have a 0 on one side and all the other stuff on the left-hand side. So you can write x squared equals 7 as x squared minus 7 equals 0, and it is the same equation. Anything that solves equation 5a will solve equation 5a prime, and vice versa. Same for 6a and 6a prime. Okay, which brings us to throwing random numbers around with these x's, x squareds, and x cubes, and I could have written much longer ones with x to the 4th, x to the 5th, x to the 7th, x to the 257,000 million. All these things that we call polynomials. And a lot of them have nice rational real number solutions. Some of them have solutions that are not rational numbers, but are still in the real numbers. This top one, if memory serves at all, x can equal 5 there. So looking at that quick, if we stick in x equals 5, x squared would be 25. 3 times 25 is 75, minus 9 times 5, which is 45. So 45 from 75 would give us 30, and 30 minus 30 would be 0, as required. So you can check it. You stick in 5 on the left side and run through the calculations, you get 0. But it also works for x equals -2. If I stick in -2 here, -2 squared is 4. 4 times 3 is 12. And then -2 times -9 is going to give me 18. 18 and 12 is 30. 30 minus 30 is again 0. This is one of the fun and important points about polynomials. You can have more than one solution. 5 solves equation 7 there. -2 also solves that equation. And you can play around with these things and make more complicated versions of them. We've got 8, which also has some solutions. And there's whole areas devoted to finding solutions to those equations. And then we come to 9, where by some careless messing around with the equations, you can write down something like, well, what if I have x squared plus 4 equals 0? And suddenly, again, this is one of those things where for some period of time in the history of the world, few hundred years, people basically lost their minds over these kinds of things. A lot of people said, that's crazy, there's no such number, there is no way that you can have a number that when you square it and add it to 4 equals 0. You've got to restrict people from randomly moving coefficients and numbers around in equations because they're creating nonsense. And other people said, well, what if we pretend for a little bit that this isn't nonsense, that there actually could be a number that would solve this thing? Just like we kind of, for a while, pretended there were solutions to things like 5a, and it didn't seem to hurt us, and it actually led to interesting mathematics. Or we started saying, what if there were solutions to things like 1a, and it didn't hurt us to believe in negative numbers, and it led to interesting mathematics. So the complex numbers were created, or the imaginary numbers. There's a very slight distinction between imaginary numbers and complex numbers. In theory, an imaginary number is one that's purely made up of some multiple of the square root of -1, whereas a complex number, which we usually call the square root of -1 I in this context. Whereas a complex number could be something like 5 plus I, or 2/3 plus I, or any real number plus 3i, or whatever. If it's got both a real part and an imaginary part, it's a complex number. The idea of, that's just what they call it. They call it a complex number. The idea of having a special name for pure imaginary numbers, I think, is probably some historical holdover from some period where somebody thought that was going to be an important thing. It really isn't. Generally, if you go to upper division math courses at a university, there's a course in real analysis, the analysis of real numbers, and there's a course in complex analysis, the analysis of complex numbers. There is no course on imaginary analysis, where we just do analysis on imaginary numbers, because the imaginary numbers are a subset of the complex numbers. Okay, way too much time spent on that. So in trying to solve things like number 9, the complex numbers were invented. And as I believe was mentioned in that one physics video, one of the great things that was discovered was if you allowed solutions for x to be anywhere in the complex numbers, then suddenly there was a very simple solution to the question of things like how many solutions are there to an equation like number 8. Previously, you'd had to go through all kinds of steps and jump through all kinds of hoops to try and figure out how many solutions there were, if there were any at all. And now all you had to do was look at what's the first highest exponent that x is being raised to. It's a 3. Oh, there are 3 solutions to that equation. I don't need to know anything more than that. If there was an x to the 5th term in there, there would be 5 solutions to that equation. If there was an x to the 17th term, there would be 17 solutions to that equation. Some of them might be complex numbers, some of them might be hard to find, but there's an extremely well-proven theorem that says there will be exactly 17 solutions to any equation that has x raised to the 17th power in it that is a polynomial like this. Whatever the highest power that x is raised to, that's how many solutions there are. If you have an x to the n term, there are n solutions. There I said the same thing about 5 times. And then we come to a slightly interesting case, at least it's interesting to me, and it's kind of the one that was being talked about in the physics lecture. We can look at something like number 10 and say, what if we've got something like x to the 5th power equals 1? As it turns out, in the real numbers, that has a very simple solution. Well, x is 1. That's no sweat, no problem, got it. But if we allow x to be an element of the complex numbers, yes, x equals 1 is one of the solutions, but there are 4 more. There are 5 complex 5th roots of the number 1. If you want, and at some stage I can talk about that in more detail with real examples. If I'd written for equation 10 there, if I'd written x to the 4th equals 1, if I'd written x to the 4th equals 1, there'd be 4 solutions. For the morbidly curious, so the solutions to x to the 4th equal 1, there are 4 of them, obviously, again. You would have one of them is x equals 1, then there's also x equals negative 1, then there's x equals I, and there's also x equals negative I. You take negative I and you square it, and then you square that result, you get back to 1. The x to the 5th equals 1 case is actually kind of interesting because they end up with fancy little square roots in them, and multiplying them out to verify that you've got the right answer can be a huge pain. But that's a topic for another time. The important point here is that at some point, somebody was looking at that and realized, hey, if we let x be part of the, if we say x is an element of the complex numbers, then we get 5 solutions where we thought we only had 1 solution previously. Which brings us to 11, which I'm only going to discuss briefly. Apparently, fairly recently, like within the last 50 years at least, or maybe the last 70 years, but that something like that. Somewhere maybe starting in the 1950s, I don't really know. I'd have to go look it up. Somebody started looking at the equations like number 11 here and saying, well, hey, wait a minute. At some point, we did a crazy thing and said, what if there are actually 5 solutions to x to the 5th equals 1? Well, if we do something even crazier and suggest that there might be 5 solutions to x to the 5th equals 0. And presumably 6 solutions to x to the 6th equals 0, and so on. I don't know too much about this area of mathematics. In fact, I don't even remember what it's called. I do remember reading about it. And it's a significant area of modern mathematics that goes into the study of some very advanced topics in physics. I have friends who understand this area of math much better than I do. As I say, I've never had a course in it. I didn't even have time to look it up this evening to see what the name was. But apparently, yet another new interesting set of numbers beyond just the imaginary / complex numbers and into something more exotic, crazy numbers, I don't know what they call them, where the idea of having more than one root of 0 was introduced. And we'll circle back around to that very shortly. And also, just for fun, I wrote down we can have, in modern mathematics, equations like number 12, 5x equals 0, which when solved, you then normally just get x equals 0, and that's all great. 5 times 0 is 0, therefore x equals 0 is a solution for that equation. And we will look very briefly at 13. 13 is the exception to all this. This is the point where it breaks down. If I write down 0 times x equals 5, as an example, or 0 times x equals anything, really, even 0 times x equals 0 is a little suspect as an equation, but 0 times x equals 7 doesn't work either. This basically is one of those equations that leads to a divide by 0 error. And tempting, though, is to think, ooh, hey, sorry, I had to pause for a moment. Tempting, though, it is to think, oh, hey, maybe this is an opportunity to create a vast new field of mathematics that nobody's thought of before, where I'll be the first person to say, I'll explore this strange new area by assuming that it's not crazy to solve for x when 0 times x equals 5. People have tried, and circling back around, as I said, the one thing that every other equation on this page has in common is that you can do mathematics starting from the idea of something like x to the 5th equals 1 has more than one solution, or x squared equals -4, which is basically what number 9 is saying, and you get self-consistent mathematics. Mathematics that does not contradict itself. It can look weird, it can be very complicated, it can be the sort of thing that makes you want to pull your hair out because it seems counterintuitive at times, but it is self-consistent. It obeys the laws and rules of logic. There is no known way of doing an equation like 13 with 0x equals 5 and have it be self-consistent into anything that doesn't run into constant contradictions, self-contradictions, and basically falls apart. These other things blossom instantly into very nice self-consistent theories of mathematics. 0x equals 5 blossoms immediately into gibberish, and nonsense is too nice a term for it. It instantly, an equation like this instantly leads to basically being able to prove that 1 is equal to 2, that 2 is equal to 3, that 3 is equal to 4, and that everything is equal to everything else, and also that all of them, also that 2 is not equal to 2, and so forth. You could potentially say, well, there's something very profound to be learned there. Or you could equally say, no, that's just complete insanity. There are some even fairly sophisticated proofs to, and some not so sophisticated proofs, all of which, again, in looking at number 13 there, say that not only is that equation not consistent with our existing mathematics, that it isn't self-consistent with any mathematics. It would be essentially like writing down the equation x is not equal to x, which might lead to some interesting Eastern transcendental meditation. In fact, I've meditated on that a few times. The unique x such that x is not equal to itself, but it doesn't lead to very much in the way of mathematics. Okay, and then there's this little bit of gibberish that I put over on the side here, where we've got x equals 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/32 plus so on. And there's a question, or was a question at some point in mathematics, should things like that be allowed? Was that a number, or was that something other than a number? All the ones that I've written down here, at least, converge, as it's called, to specific answers. If you have interests and or questions and or doubts about that, we can go into that some other time, but the first one actually converges to x equals 2. The second one converges to a number. I don't actually remember what it is off the top of my head, even though I saw a video on it and worked it out just the other day. It's a nice number. It's like pi over 6 or something like that. And then the bottom one is x equals 1 over 0 factorial plus 1 over 1 factorial plus 1 over 2 factorial plus 1 over 3 factorial, and so on. 0 factorial is, for reasons of convention that we don't need to get into here, is basically defined to be 1. And then all the other factorials are just, as I've written down a little below that, 4 factorial is just 4 times 3 times 2 times 1. 5 factorial is 5 times 4 times 3 times 2 times 1. 6 factorial, etc. Interestingly enough, it's worth noting 5 factorial is obviously just equal to 5 times 4 factorial. And each of the others works the same way. 6 factorial is just 6 times 5 factorial. So 4 factorial is actually 24. 5 factorial is 5 times that, or 120. 6 factorial is 6 times 120, so 720, and so on. The reason I include this at all is that bottom one, x equals 1 over 0 factorial plus etc. If you start adding that up, you get the number that we usually call E, sometimes called Euler's constant, but there are about 3 other constants that go by that name, so it's usually just called E, the base of the natural logarithm system. And it turns out that there's a fairly straightforward proof that, as I've written there, if x equals that sum, if x equals E, then x is not a member of the rational numbers either. In fact, I could have gone beyond that. Not only is E, this number that you would get if you summed up all of those things, not only is E not a rational number, like with the square roots, which are not rational numbers, it also isn't an algebraic number. There is no polynomial, like the kind of things that are written down in 7 and 8, which will give you E as the answer to that polynomial. unless the polynomial happens to have e as one of its coefficients. But there's no polynomial in real coefficients that will give you e. There's a whole class that I kind of skipped over that they call algebraic numbers, which are really just sums and divisions and multiplications of the irrational numbers, the square roots. So things like 5 times the square root of 3, that would be an algebraic number. It turns out that e isn't even among the algebraic numbers. It's part of the real numbers, this funny stylized r that I've written up there next to 7 and 8, but that was kind of overkill. I could have 7 and 8 would actually have solutions in the algebraic numbers. So I skipped a step at some point, is I guess what I'm trying to say there. E is an interesting customer. It's a positive number. It's approximately equal to 2.7182818. And then even though it looks like it's about to repeat, it doesn't. It's just like pi. It goes on forever and never repeats. And because it's an algebraic number, there's essentially no short way of writing it down. You can't just say, well, it's equal to the square root of 7 over the square root of 3. No, it isn't. It's equal to the sum of an infinite number of numbers, which thankfully the numbers in that series get small very quickly, so you can approximate e to however many decimal places you'd like in a big hurry, but trying to actually write it down is frustrating. Let's just leave it at that. But it turns out there are a whole bunch of real numbers that are not rational numbers. They're not integers. They're not rational numbers. They're not even algebraic numbers. They're these transcendental numbers that are usually written down in terms of the sum of some kind of infinite series. So, wrapping this up because this became way longer than I wanted it to. I'll come back in the next thing that I record and talk about the significance and usefulness of I in physics in particular, to the extent that I understand it, which is considerable but certainly not complete. But I guess I just wanted to do a little bit of reasoning by analogy here. Definitely don't reject I as being a useful concept just because it seems a little outlandish or not a number in the same sense that we're used to thinking of in everyday terms, because it would be really easy to dismiss something like pi and say, well, that's not a real number. That's, you just made that up. That's 1, 2, 3 pi. That's not how you count. Makes about as much sense as 1, 2.5 apple. And yet, I'm pretty sure most of us will concede that the concept of pi is enormously useful to engineering and everyday considerations. If I wanted to paint the outside of the cylinder, I would have to know and have some appreciation for at least the approximate value of pi. If I've got a circular plot of land, I need to know that the formula for the area of a circle is pi r squared. Again, you need to know at least the approximate value of pi. E and I, these other numbers that we use a lot, fall into kind of that same category. It would be really easy to dismiss pi and say, well, it's not a rational number. It's not even an algebraic number. How do you know that this thing even exists? It's amazingly useful. So it doesn't really matter whether it exists. It's sort of a philosophical question. Does any number exist? Greek philosophers went on at some length about, show me the concept of threeness in its purest form. You can show me lots of examples of sets that have three objects in them, but what is threeness? Philosophers, and to some extent mathematicians, can argue about those things until their heads explode. Physicists and engineers tend to be more practical and simply say, I don't really care what a number is. I don't care what the concept of number means. I don't care if pi exists or if 3 exists or if 2.5 exists. What I care about is getting results, and if knowing that the square root of 2 is approximately 1.414 will allow me to quickly calculate how far it is from point A to point B, then I don't really care about the philosophy of, is any of it real? It's real enough if it gets me an answer that actually works in the real world. So right there at approximately an hour, I'm done talking about whether I exists, why it exists, and in the next babbling session, I'm going to get into what is I useful for, what does it mean, what do we do with it once we've basically just accepted it as something that we're going to be using in our math. Once we've accepted it, adopted it like a little puppy and brought it in, what can we do with it? That's going to be my topic for next time.